Okay, so we've studied accelerating clocks, and we're ready to understand an accelerating reference frame. Okay, that's the Rindler wedge, which I promised to get to you now. Okay, so we had for the clock, okay, that x squared minus ct squared was equal to c to the fourth over g squared. Okay, but now I can imagine instead of that particular case, I can imagine placing clocks all along the x-axis. Okay? Okay. Well, if I do that, then the hyperbolas for all of these different paths for the different clocks is going to be x squared minus c squared over t squared equals the position of that clock squared. I'm referencing the position of that clock squared relative to the special one, which was at c squared over g, and I'm calling that x tilde equals 0. And so I'm writing these that are different x tildes, okay, as this. Okay, I want to have x for the frame S. I want x tilde for a different frame. Okay, okay, okay. So there are my clocks. I have a whole bunch of clocks along the x frame, and all of those clocks are experiencing a proper acceleration. Okay? Well, what is that proper acceleration? Okay? Well, I see that as I move the clocks out in this direction, the proper acceleration is no longer g squared over g, c squared over g. No, I move them further along. For the one at the position I called x tilde equals 0, the proper acceleration was c squared over g. Okay, the proper acceleration of these guys is c squared over g of x tilde, which is equal to x tilde plus c squared over g. Okay, which I just read off the picture. Okay, I just read that off the picture. Think of each, but I'm going to then think of each of these clocks, okay, as a space-time path of a point on a huge mothership. And I'm going to measure the distance off the mothership floor as x tilde. Okay, so here it is. Okay, so I imagine that when t is equal to 0, I measure the mothership's distance as x tilde. I want to distinguish that from x, right? Because x is the coordinate in my inertial frame, which ain't moving. But now my rocket ship is going to start moving because the different points of it have acceleration, proper acceleration of, well, if x tilde is 0, the proper acceleration is g. If x tilde is over here, the proper acceleration I read off from this. Okay, so what I want to do is to set up a coordinate system, okay, for this wedge between the light cones, okay, which describe accelerating points. And I want to imagine, and I want to see if it works, that I can make that accelerating frame to be a rocket ship. Okay, where there's an acceleration appropriate to every point in the rocket ship, so that at any particular moment at that rocket ship, the rocket ship has a common velocity of v. Okay, so it moves in a stress-free fashion to the left. Okay, so I think of each hyperbola as a space-time path of a point on a huge mothership. Okay, like in the Star Wars movie, and I measure the distance off the floor as I go off the floor as x tilde. And here's my rocket ship, and here's x tilde shown there. So this is really a very big rocket ship. I cannot approximate it by a point. It's going to cover my whole region. Okay, right. So therefore, I have a definition of x tilde. I want to understand t tilde in that rocket ship. I want to understand simultaneity in that rocket ship, so I can make measurements in this new coordination. Okay. Okay. We do this all the time in Euclidean physics, right? When you, for example, take a sphere and you want to coordinatize it, what do? Well, you might use polar coordinates. You put down polar coordinates around the North Pole. Okay, they're curvilinear coordinates. okay, and you learn to do your geometry with those curvilinear coordinates. Okay, they're not as convenient as Cartesian coordinates, but they suit the curvature of the sphere. Now what I want to do is to imagine okay, a rocket ship moving to the right with a common velocity v. That means different parts of it are going to have different accelerations, which are going to depend upon the height of the rocket ship, okay, and that will coordinatize, okay, the wedge between the two light cones. That's what I'm doing here. Okay, so I want to understand that grid. So I'll take one of my hyperbolas, okay, which read x squared minus ct squared is equal to a constant, and I'll differentiate it with respect to time. And that's what I've done here. Okay, dx by dt, I want that to be a velocity v, the velocity of the rocket ship. And so I learned that t, okay, is related to x by v over c squared x. Okay, well, you know what? That's a formula I've seen an awful lot in this course. Okay, that reminds me of the relativity of simultaneity. Okay, this is a slice through the Minkowski diagram, okay, at a constant angle, okay, where t, okay, where t moves up as a function of x. To make that explicit, consider the Lorentz transformation to the ship having an instantaneous velocity v. Okay, the Lorentz transformation reads like this, right? So if I take what I want, which is the velocity of a hyperbola, okay, which was the hyperbola moves so that any point on it had a t related to x by this. I see that sets actually the time in the new frame to 0. Okay, so the line t equals v over c squared x is a line of constant tau prime. These are rays from the origin, and a line of constant t tilde is a line of constant velocity, right? That's what the definition is, constant velocity. Same velocity for every hyperbola, okay? And so the tangents to the hyperbola look like this. Okay, so the picture isn't very good, but there's a better picture in your supplementary lecture 11, okay, which shows that all of the hyperbolas like this, okay, at a particular t tilde being t equals v over c squared x, cuts through here, okay, have a common velocity v. That's just the tangent to the hyperbolas, and they're all parallel, as you see from this arithmetic. Nothing fancy whatsoever. Okay, but what does that mean? See, my rocket ship at time t is equal to 0 was at rest, right? All of these hyperbolas were perpendicular, okay? All the velocities were equal to 0, okay? But every point in my spaceship had a particular proper acceleration, okay? And the proper acceleration was written down before, okay? And then I see from this arithmetic, okay, that if I move, that as the rocket ship moves, okay, the line of constant time in the rocket ship swivels up, okay, and it swivels up in such a way, okay, that every point on the rocket ship has a common velocity v. Actually, that's obvious. Why is that obvious? Well, okay, these are hyperbolas, and initially they had a common velocity of 0, okay? But they're invariant hyperbolas. They're invariant hyperbolas. So if they have that relationship at t is equal to 0, they're going to have that relationship at any other time. So at any other time, they have to have the same velocity. And that's all that the arithmetic shows. Okay, but that's critical, right? Because that means that if I set up my rocket ship so that the different points follow hyperbolas, okay, invariant hyperbolas, okay, then every point in my rocket ship has a constant time, okay, has a constant velocity at a fixed time in the rocket ship frame. Okay, so my rocket ship doesn't fall apart. It doesn't get stressed out. Okay, and that's critical. And that's just this little bit of arithmetic here. Okay, okay, and that's said here. So all the points x tilde along the mothership have the same velocity at any time t tilde in the mothership's resting frame. And I, like I say, that's just a fact about invariant hyperbolas. Okay, so the mothership accelerates without internal stress. Okay, so I can identify the proper acceleration of different points of the mothership. Okay, just on the right hand side of the previous equations, I write it c squared over g, but now I let g be a function of x tilde. And how does the right hand side of the equation work? Well, it was just x tilde plus c over g. So I learned that the proper acceleration as a function of the distance up my rocket ship falls like g over 1 plus g x tilde over c. Okay, okay. This guarantees, as we said, that the Lorentz contraction of the ship is given by a global transformation law, delta x equals x naught over gamma of v, right? Right? We engineered the whole construction so that at any particular proper time within the rocket ship, that all of the bits of it are moving at a constant velocity v. Okay, that means, of course, that the whole thing contracts with a common factor of gamma. Okay, that's great. So what that also means that its top must accelerate less than its bottom to accommodate a constant velocity. Well, that sounds really obscure. That ain't so obscure when you look at that picture. Look at the picture here. Here's constant time in the rocket ship. Okay? Well, it's pretty clear that the higher you go up in the rocket ship, okay, the proper acceleration is less than the proper acceleration down here, right? Okay, that's self-evident. That was self-evident on this axis, where the proper acceleration went like the reciprocal of the distance off the distance off the t-axis, and the details are just written down. Okay, here's the details, right? Here's the details. Okay, so here are the hyperbolas like that. Okay, and so I learned if those are the hyperbolas, okay, then I see that the individual coordinates have got to satisfy this transformation law. Okay, we already saw, okay, that for t equals 0, x has to be x tilde over c squared g, and that's contained in this transformation law, right? Because when t tilde is equal to 0, the cosh is equal to 1, and so x is equal to c tilde over c squared g. But then in addition, I have to be on this invariant hyperbola, and so t has to be given by the same prefactor times the sinh, because plugging this into the invariant hyperbola would give me the correct right-hand side only if the coefficients of both of those equations are matching. Okay. Not such a big deal. Okay. 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 So now we understand, okay, the wedge, okay, this region of space-time between the two light cones in these terms of the space and time measurements on invariant hyperbolas. So we can use x tilde and t tilde to parameterize Minkowski space for x tilde greater than 0. And this is an interesting exercise to do. And the details are left to your supplementary lecture. I remind you, we're just describing Minkowski space. We're doing special relativity. So we're always in Minkowski space, okay? But we're dealing with accelerated clocks and accelerated rods. Okay, so ds squared is equal to this. And in my new reference frame, it's equal to a metric times x tilde, with mu and nu appropriate to that. But now I know what x is as a function of t tilde x tilde. I know what x is in terms of x tilde t tilde. Here it is, okay? And so I can take the differential of dt in terms of x tilde and t tilde. I can do the same thing for dx in terms of x tilde and t tilde, and do some arithmetic. That arithmetic is in your notes. Okay, look at supplementary lecture number 11 that coincides with these video lectures, and you'll see that the Minkowski metric, lo and behold, is 1 plus g x tilde over c squared, quantity squared, dt tilde squared, and the spatial parts are left unchanged. Okay, so I've suppressed dy and dz, but they could be here as well, and they would just be Euclidean. Okay, the only place I find a modification of Euclidean metric is in G00, and here it is. This is the metric of the Rindler wedge. No, so I can check a few things about that. First of all, you see I find a new parameterization of Minkowski space which looks rather interesting. Okay? Okay? Okay. So recall from the textbook that we showed in a static space-time, you could always write the metric in the form of e to the twice phi over c squared dt squared minus the spatial metric. And that's the kind of thing we found here. The spatial metric in this case is just good old flat Euclidean space. So let's find phi in terms of x tilde. I see what it is here. Okay, this creature here is just e to the 2 phi over c squared, and so I can calculate for you the Newtonian potential. It's c squared log of 1 plus g x tilde over c squared. Okay, well that sounds a little bit funny, but of course in Newton's world all the physics is in the forces, so I don't care so much about phi. I care about the gradient of phi. Well, how do I take the gradient of phi to form the acceleration? I got to be careful, right? Because in a curved space-time, my Christoffel symbols come into play. But what about this situation? There's no curvature here. My spatial metric is good old flat Euclidean. So I can just take my gradient of phi and expect to get the proper acceleration. And lo and behold, I do that. I take the gradient of this logarithm. I get g over g plus g x tilde over c squared. And that's exactly what I had before, just thinking in terms of my hyperbolas. Okay, so we come full turn, we've come back and found that the proper acceleration is given by this formula. So an astronaut on a mothership feels a proper acceleration which diminishes as you go up the rocket, and we understood that. Okay, the proper acceleration has to diminish as you go up the rocket so that all of the points in the rocket, okay, have a common velocity v. Okay, that has to be compatible with the relativity of simultaneity, and we saw that in our Minkowski diagram. Okay. So that's good. So the Rindler wedge is a kinematic model. Is a parameterization of Minkowski space, but I can think of it as a kinematic model of horizons. Okay. So here in the wedge, number 1, I can imagine a point, a particle which moves outside like this. If it moves through the light cone xc. Well, what about that? Well, when it moves outside, okay, that light cone, it can't communicate to any of the inhabitants, on the accelerating rocket ship, right? Because that would require a velocity greater than the speed of light. And so the future light cone acts as an event horizon. It's a one-way surface. When something goes through it, it can never come back. It can never communicate back with anybody accelerating on the Rindler wedge. Okay, so the Rindler coordinate system is often used in the vicinity of the event horizon in a real space-time of a black hole to simplify the kinematics. Okay, and that's what's done here. Okay, but it has limitations. For example, but 1 is just a reimagining of Minkowski space. Okay, so the basic metric here is good old Minkowski. It's flat. It's flat as a table. There are no tidal forces in it. Its curvature is everywhere 0. Okay. Well, if you go back to the formula, you know, you had an x tilde dependent term in dt tilde squared. So how does that work? Well, it's clear that there's no curvature in the Rindler wedge because, for example, I could be one of those astronauts on the Rindler wedge accelerating like mad, and I can look for curvature. How would I look for curvature? Well, I'm not going to do a calculation, okay? I'm just going to do an experiment. My experiment will be to drop a couple of test particles. And what am I going to look for? I'm going to look for tidal forces, okay? Okay, I'm going to look for geodesic deviation, okay? But in the Rindler wedge, you saw that all of the effects are in the x tilde direction. There's nothing acting in the transverse direction, so they fall to the floor, okay? And their transverse direction, transverse separation, is a constant. So there's no tidal forces. There's no curvature. Okay. There's no curvature. Okay. So I think that's as much as I can get out of the Rindler wedge. I think it's very instructive, and there's more to be done with it, more applications to be done with it. And so check that out in supplementary lecture 11. And next time we'll turn to a different special topic.